Hi everyone, my name is Suraj Malladi. This is joint work with Matt Jackson and David McAdams, and the title of this presentation is Learning Through the Grapevine, the Impact of Noise and the Breadth and Depth of Social Networks. People often learn how to make a variety of decisions from secondary sources, like whether or not to vaccinate their children or start a new diet. And often the sources that we consult, like journals and newspaper articles and friends and colleagues, might have themselves obtained their information secondhand from other sources. It sometimes happens that there's consensus among primary sources on a particular issue, despite the fact that there's significant disagreement elsewhere in the population. So for example, 40% of American parents have delayed or denied vaccinations for their children, and 27% of Americans don't believe in climate change, despite the fact that these are two issues for which the scientific community seems to be in consensus. These large disparities on seemingly objective issues seem to reflect the fact that there's significant noise and bias in the way information gets communicated down from primary sources to the population at large. While noisy and biased communication is certainly not a modern phenomenon, online platforms have facilitated long chains of noisy message passing, and by now we have a lot of evidence documenting how frequently messages that get shared online can mutate, whether unintentionally because someone along the way misunderstood what they heard, or deliberately because a biased agent wanted to corrupt the information in one direction or another. Regulators around the world have become increasingly interested in coming up with policies to combat misinformation and disinformation that spreads in online channels, but in many democratic countries an equally important question is who should be the ones responsible for directly implementing these policies aimed at curbing misinformation. The concern is that if governments get involved in the business of censorship, they can overstep their bounds and encroach on traditional freedoms like freedom of press and freedom of speech. So in France, for example, recent anti-election misinformation laws raised concerns that these could give ruling parties leeway in silencing political opponents. If governments don't get involved in directly determining what can and cannot be said, the other natural candidate to play this role are the online platforms themselves, but they also resist this role of actively policing the content that's trafficked over their channels, and Mark Zuckerberg was recently quoted saying, "I don't think that Facebook or internet platforms in general should be arbiters of truth." In this paper, we ask what are the effects of noise on learning, and what are information-agnostic ways of improving learning, where by information-agnostic, we mean those policies which don't require knowing what is the actual content of messages that are being sent out. The value of such policies is that they're neutral, they don't require the implementer to actually take a stance on what is or isn't truth. They can be implemented by an uninformed platform which can't tell apart misinformation from true messages, and they can also be implemented by platforms which can't directly observe the messages that are being sent because they respect user privacy. To give a preview of our answers, we find that learning is possible from distant sources if receivers are certain about the rates with which messages get mutated. Of course, whether or not learning actually happens depends on how many sources receivers have access to, or equivalently, how broad are their information networks. However, only in this knife-edge case, where receivers are absolutely certain about the rates with which messages get mutated, can they make up for the loss of information arising from noise by consulting additional secondary sources. It turns out that, in general, with even slight uncertainty about these mutation rates, learning is going to be impossible from distant sources, and this can offer an explanation for why people who start out at different priors might get stuck at those priors despite the preponderance of communication on a particular issue. Next, we find that we can restore the possibility of learning by reducing the average distances that messages travel between primary sources and receivers, since this gives less of a chance for noise to creep in along the way. But if limiting the distances that messages travel is not a tool directly under a policymaker's control, they can achieve similar results by reducing the breadth of information networks, for example, by limiting the number of times that users of a particular communication platform can forward a given message. One effect of a policy like this is to reduce the average number of messages that platform users hear, but the policy eliminates more messages originating from distant sources from reaching a receiver than messages from nearby sources. So while receivers hear fewer messages, what they hear has a higher signal-to-noise ratio, and the second effect can overwhelm the first for an appropriately designed forwarding cap. In the next part of the talk, I'll discuss our model and then state our results on the effects of noise on learning. And then I'll present our main findings on information-agnostic policies for improving and restoring learning. We consider a simple model in which the state of the world omega is either a 1 or a 0, and you can think of this as encoding climate change is real or climate change is not real. The ex-ante probability that the state of the world is 1 is denoted by theta. Messages also take the form of 1s or 0s to reflect the underlying state, and there's a chain of message passing agents 1, 2, all the way up to t, and we call 1 the primary source, it's the first agent along this chain, and T, the last agent along this chain, is the receiver. The timing of the model is as follows. First, a primary source sees a signal of the state and then passes this message along. This message may or may not transmit, and if the message does survive, then it might survive in a mutated form, so a 0 that was sent out might be heard as a 1, and a 1 can become a 0. Now, if the message survives to reach the next agent, then he also tries passing it along, again subject to the same forces of noise and communication. And finally, the receiver T sees the available evidence and then updates her beliefs about the state of the world. And the available evidence can take the form of a 0, a 1, or no message at all if the message died somewhere along the way. Noise in this model takes the form of mutations and transmission failures. And mutations, as I mentioned before, is 0s becoming 1s or 1s becoming 0s. And there's a chance μij that a message of type I mutates into a message of type j when it gets transmitted from one agent to the next. A message I heard by one agent is then received by the next in a message passing chain with some probability pi. And p sub I being less than 1 means that the first agent didn't care to pass this message along, or the second didn't hear or pay attention to what was said. In this paper, we allow the rate of transmission failures to depend on the content of the message, but for the talk, type 1 and type 0 messages get dropped at the same rate. Finally, mutations and transmission failures occur independently at each step of communication. So far, we've been considering what happens along a single chain of message passing, but in practice, people might have access to multiple chains of messages. To capture this, we allow messages to arrive through some information network for each receiver, and this information network we model as a depth T tree with n leaves, where the leaves are the primary sources of information and the root is the receiver, and each path from the leaves to the root is a message chain. Our main object of interest are the beliefs of the receiver conditional on the messages that she hears through her information network. More formally, B and T denotes the posterior belief of the receiver that the state of the world is 1, conditional on the messages that she receives through a depth T tree with n leaves. Here's an example of a simple information network. It's a depth 4 regular tree with 8 leaves. The leaves are the primary sources, and the root, highlighted in blue, is the receiver. In this example, the state of the world is 1. This information gets noisily communicated to the primary sources. Most of the sources hear 1, but the 4th leaf hears a 0 because of a mutation, and the 5th leaf hears no message at all because of a transmission failure. These primary sources communicate their information noisily to the nodes at the next level, and again you have transmission failures and mutations. This information gets communicated down one more level. Finally, these messages reach the receiver. Of 8 initial signals which were sent out, 4 ultimately reach the receiver in some mutated form. 3 of these signals are a 1, and 1 of these signals is a 0 message. The main positive question we want to address is, can the receiver learn from distant sources? Or to ask it in a different way, how quickly does the number of message chains have to grow as the distance to primary sources grows in order for the receiver to learn the true state? To answer this, it's useful to define the concept of a sharp threshold. We say F is a sharp threshold for learning if 2 conditions hold. First, the agent learns the true state, meaning her posterior beliefs converge to a point mass, whenever the receiver hears from more than f of t chains in the limit. And second, the receiver learns nothing, meaning her posterior belief even after observing all her messages is close to her prior, whenever she hears from fewer than f of t chains in the limit. An initial finding is that when the receiver knows the mutation rates, sharp threshold for learnings exist. So for random trees, where the number of direct contacts that each node has is an IID draw from some distribution, this lemma says that receivers learn fully whenever the average degree is sufficiently large, and they learn nothing otherwise. So sufficiently broad networks allow receivers to overcome noise. However, it turns out that this result on the possibility of learning is very fragile. So suppose that these mutation rates aren't known, and instead the learner has an atomless prior on the ratio of mutation rates, and this prior has a connected support. This is a very weak assumption since, in particular, it includes the case of a receiver who's almost certain about the mutation rates and has a prior of support length epsilon. Then it turns out that there's no learning in the limit. No matter how many chains the receiver has access to, she can't learn in the limit as the distance to primary sources grows large. So any uncertainty about mutation rates makes learning from distant sources impossible. Given our impossibility result, our next set of questions will be about what policies we can use to restore learning. So far, we assume that messages only originate from distant sources, but in practice, we might hear primary information that arises both nearby and far away from us in our networks. Now, this possibility alone doesn't restore learning, because if the messages that we hear through informal social learning channels don't come tagged with their origins, we might still get swamped with too many distantly sourced messages, and we can't tell which ones are noisy and which ones are more accurate, and so we might end up not learning very much. The question is whether or not there are any interventions that a platform can use to restore learning and ensure most of the information passed through its channels are correct. One idea is to limit the distances that messages travel so that receivers can be sure that whatever they hear is going to be of high quality. And Proposition 2 describes how a planner can set these distance caps. Proposition 2 says that messages that originate closer than some t-star steps away are more likely to be true than false, regardless of the state. But messages originating farther than t-star steps away are more likely to be false in some state. Now, t-star is just a function of the mutation rates, so a planner who only understands how noisy information can be on its channels, but doesn't know which state is true and which state is false, might try capping the message distances below t-star to ensure that most of what is communicated over its channels is actually going to be true. While capping distances is ideal, it might not be possible for platforms to keep track of and discard messages that originated far away from receivers. For example, a platform might not even be able to tell whether a message is a mutation of an earlier message or if it constitutes a new piece of information. And in other cases, the platform might not even be able to read the messages that are being sent over its channels if they're encrypted. In these cases, Proposition 3 suggests a way of using the idea of reducing distances in a more roundabout fashion. Suppose for simplicity that information networks are regular trees, and suppose that mutation rates are not symmetric. Then the expected number of true messages that a receiver hears is greater than the expected number of false messages if and only if the degree of the receiver's information network is sufficiently small. The graph here illustrates Proposition 3 using simulations. Each line in this graph represents information networks of a fixed depth, and the x-axis varies the breadth of these networks. So each point on the line represents an information network of a given breadth and depth. Now, in each of these information networks, every node has access to a primary signal, which it forwards, and each node also acts as a noisy communicator of the other messages that other nodes have passed down to it. The y-axis shows, in a given state, the probability that most of the information heard by the receiver in a given information network is correct. So what this graph then shows is which information networks are more or less conducive to the receiver hearing accurate information. For relatively shallow information networks, like the depth 1 and depth 5 networks in blue and red, having more breadth always increases the chances that more messages heard are correct. But for depth 9 and depth 10 networks, there's a sweet spot. Beyond having breadth 5 or breadth 6, the number of unreliable distant messages starts to overwhelm and the quality of information deteriorates faster than the quantity of messages heard makes up for it. Proposition 3 suggests that capping the breadth of information networks can restore learning, and the reason is because it reduces the average distances that messages heard by any receiver travel. Reducing breadth cuts down the number of messages that receivers on a platform hear, but it also creates a positive selection effect. The policy increases the rate with which farther away messages die out due to transmission failures more than it increases the rate with which closer messages die out. So what the receiver ends up hearing has a greater fidelity to its original sources. Unlike capping distances directly, it's easier to implement a platform that restricts the breadth of networks by, for example, limiting the number of times users can forward a given message. A policy like this also restores learning and is information agnostic since implementing it doesn't require knowing anything about the true state. And finally, it can even be used by platforms which encrypt the messages that their users send. In fact, this cap on message forwards was exactly the policy that WhatsApp adopted in response to criticism that it was a vehicle for the spread of misinformation during Brazilian and Indian elections, and in reaction to reports that misinformation that spread on WhatsApp led to incidents of violence in India. And more recently, WhatsApp tightened their message forwarding cap further after observing several conspiracy stories and false health information related to COVID being forwarded on the app. To recap, we talked about how learning is possible with sufficiently many secondary sources when receivers know the mutation rates. When these mutation rates are even slightly uncertain, then learning from distant sources becomes difficult, and any platform that facilitates communication through longer chains will worsen the conditions for learning. A way around this is to limit the depth, or if that's not possible, the breadth of information networks, and the value of such policies is that nobody has to play the role of arbiter of truth in order to implement them. That's it for this talk, but we push our model further in the paper and also analyze the case where, in addition to the content of received messages, the frequency of communication can also be informative about the state. And communication frequency can be informative if type 1 messages are less or more likely to suffer transmission errors than type 0 messages. To give an example of when this kind of thing can happen, a message that a particular scientific experiment delivered a significant result is more likely to get passed along or published than a message that the result was insignificant. We compare learning from message survival and message content and find that, always in the limit, all information comes from only one of these dimensions, which among other things suggests that simple rules approximate Bayesian learning. We also talk about how our policies of reducing depth and breadth of social networks would improve learning in this case as well, so if you're interested, please take a look, and thank you for tuning in.